Thank you. It certainly is a pleasure to be here and give you some idea of the kind of research that I've been involved in. When you hear the term alien worlds, probably the first thing that comes to mind is another planet like Mars, or perhaps a deep sea ocean vent with these crushing pressures and exotic forms of life. What I'm going to be talking about is another kind of very strange world, but much closer to home. It's all around us and inside us, and that's the world of molecular machines, such as these machines inside leaves all over the place that collect sunlight and make chemicals, or these little protein motors that walk along tubes inside our cells and transport cargo. What I wanted to describe to you a little bit about is why and what these molecular machines are, a couple of the unfamiliar aspects, that is why I call them alien worlds. I picked one example of the research that I've been involved in dealing with these robots, and then step back a bit and give some ideas of how we might go about exploring these worlds and some ideas that I wish people had told me about STEM careers early on. But first I should say a little bit about me. I went to a high school in Spain. There were 40 students in my graduating class. There were no science enrichment programs, although I was one of the few students very much interested in science. I fortunately had teachers, as you call them at that time, who helped me create independent study class, and then also apply and attend a summer school program in physics for high school students at Cornell University. And then after that, you've heard I went to Caltech and Stanford, both in physics. I've had the fortune of being involved in a variety of different topics. I found a physics and math background has been very helpful in changing fields along the way. I've not stuck to the same one. Today I'm going to talk about molecular machines and micro-robots. So first, let's get a sense of size. The machines I'm going to be talking about are on the lower end of this, so between large molecules and cells, bacteria, and the molecular machines are just basically big molecules. The micro-robots I'll be talking about are roughly the size of bacteria. And there are also today what people can make out of DNA, through DNA origami, you might have heard that term, to make interesting structures that are roughly intermediate in size and capabilities. One example is a DNA-based drug delivery robot that detects, it can do a little bit of logic to detect the right environment, opens up and delivers a drug. Another one is like a warehouse sorting robot that can sort individual molecules on a surface. Actually doesn't require any power. And then just to show that research can be a little bit more fun, this was a group in Israel that put together some DNA robots that mimic a robot story that Isaac Asimov wrote many, many years ago. Every field has its jargon, and it can be confusing for outsiders, and one of those that comes up here is, what do we call these robots? So DNA robots, roughly nanometer in size, makes sense to call them nanorobots, nanobots, what have you. The robots I'm talking about, which are still theoretical, we cannot yet build them, are of the micrometer size, makes sense to call them micro, but people often use the term nanorobots to cover this whole range. And similarly, micro-robots go up to robots that you can actually see, insect-sized robots. And this is just a potential confusing terminology, so if you hear the term, you just got to look a little bit further to see what people mean. So for instance, microscopic robots and those that, okay, that animation didn't quite work. Okay, those robots that are just too small to see. The concepts are the same, just the terminology can be a little confusing. People use it different ways. I described some natural molecular machines earlier, and then, of course, we want to engineer molecular machines to do certain kinds of tasks for us. And this is kind of analogous between birds and airplanes. They both fly. The airplanes are the engineered ones that we design for our own purposes. One that I have been working on a couple of years ago is a design for a mechanical molecular computer. Now, this might seem really odd because we're so used to electronic computers. The real advantage of this mechanical computer is small size and particularly very, very low power. And the reason is this moves and rotates on single molecular bonds, which have extremely low friction, that they don't dissipate much energy, compared to electrons, which are moving through resistors and they get hot. And you probably noticed if you use your laptop on your lap for a long time, it can get pretty hot. So these mechanical computers are not likely to be as fast as electronic ones, but much smaller and much lower power. Mechanical computers are not a new idea. It's proposed over a century ago. You can see an exhibit on them at the local computer history museum if you like. Molecular machines could have a wide variety of applications. I'm going to focus on applications in medicine, and it's very, very likely that there are plenty of other applications that no one has yet thought of, because it's very difficult so far to build and play around with these machines. What motivates me for thinking about this for medicine is basically the Goldilocks hypothesis. It comes from the story of Goldilocks and the Three Bears, that I suspect that micron-sized robots, that is, those roughly the size of bacteria, are a really great combination of size, quantity, and capability to deal with a lot of currently incurable diseases. They're small enough, they can travel through capillaries, that means they can get everywhere in the body. They can go even inside cells, because the bacteria-sized cells are smaller than our normal body cells. But they have the ability to treat cells individually. They can be numerous enough to deal with all the cells, or a large number of the cells in our body in a reasonable amount of time. And this gives you an idea of what such a future treatment might look like. This is a picture actually of just diamond powder in water, suspended in water. And you can see on the micrograph that these are all sort of jaggy particles, but they're about a micron in size, same size as the robots. And so at some point, if we can actually make these robots, this is also what a treatment will look like. It'd just be like powder in a liquid. Okay, that animation. Okay. That's numerous enough, then the third ingredient of this Goldilocks hypothesis, I think these robots can be capable enough that they can actually contain a large number of molecular machines. Now, the robots I'm talking about are tiny. Molecular machines are also tiny. It's easy to just sort of group them all together. But in fact, these robots are enormous compared to molecular machines, which means they can have a large number of machines inside them. And so if we're thinking, for example, of the kind of computational capability of these robots, a rough estimate of just how many of these mechanical logic devices you could put in them, using, say, 10% of the robot's volume, gives you sort of roughly an estimate that these robots would be like a 1980s microprocessor. So you can go ask your parents what those machines were like, but that's roughly the time when the first Macintosh came out or the first IBM PC. Nothing like the capability of your phones today, but far, far greater capability than, say, what a drug with no computation can do. Some other tricks these robots could provide is communication. They could make like a network, communicating, passing messages to other neighbors in the body. And then the ones that are near the skin could actually communicate with a device to the physician, say, here's what's going on, do you want us to change instructions, and so on. And this is a way of getting real-time information about what is actually going on during a treatment at the level of individual cells. Again, something that if you have a drug, you inject the drug and it does what it does, but you don't get any immediate way of saying, I want to change what the drug is going to do. And finally, these robots don't have to work by themselves. They could also help conventional, either adding smarts or adding precision. So now let me turn to the idea of the alien worlds. So when we want to engineer these molecular machines and robots, we have to understand the world as seen by them, not as seen by us. The first thing that's different is the physics that's important to them. If you're riding your bicycle, you probably don't even think about it, but when you're moving, you can stop pedaling for a while and you'll coast along for a while. Or when your bicycle stops, it'll just stay stopped until you start up again. And that comes from inertia. And so if you'll take in physics and you'll learn about Newton's laws of motion, objects resist change in their velocity. Now there are stories where people use small sizes. Most recently, they would be the Ant-Man movies. Unfortunately, these stories are very misleading because they apply familiar large-scale physics to these small systems. It's been known at least since the time of Galileo that the dominant physics really changes with size. And in particular, there's two things that are very different about the physics of molecular machines. One is that surface forces, friction, is much more important than inertia, and the other is thermal motion. And ironically, these are well described by Aristotle's laws of motion. This was what people understood about physics for centuries before Newton. The natural state is at rest. If you don't push, nothing happens. It just sits there. And that's not correct, but it's a very good description of what these little machines deal with. So a consequence for a robot is you cannot move the way that we do in the world. So the way we do swimming, we're not just aware of this. It really relies on inertia. And if we tried the same thing if we were really tiny, we would just go back and forth and not really make any progress. We need a different technique. Fortunately, we can learn from microorganisms which swim in a different way, and they manage quite well. But this is not the way that we would, and not the way that we could engineer it in a familiar way. The second aspect of these alien worlds is their geometry. If you study geometry, almost likely you'll be introduced to Euclidean geometry, which has been taught for many centuries. And if you think about a strange geometry, perhaps you'll think about the bending of space-time near a black hole. There are stories that involve unfamiliar geometries, and I'm happy to say that they actually get the geometry part right. If you're interested. Now, our bodies also have a very different and unfamiliar kind of geometry, and this with complex branching networks. One example is blood vessels. If you took the blood vessels in your body and just stretched them out in a line, it would more than circle the Earth. So that gives you an idea for these robots. It's a really big world inside us. Another example is our lungs. If you were to unfold our lungs, one of our lungs would take up a reasonable chunk of this room. And you get a mixing between the blood and the air. Furthermore, there's a tricky mixture of three branching networks that all have to meet at this very small level, not let any fluids mix and get out and so on. It takes about 20 or 30 levels of branching to reach that. And just try to imagine the intricate geometry of that. This is not Euclid's geometry. This goes by names like fractals. It took a long time, starting in the 1980s, for people to accept that there is this different kind of shapes and so on. So one odd thing about fractals is they can have dimensions between integers. So we're used to in Euclidean geometry, you have a two-dimensional plane or a three-dimensional solid. A fractal, in a reasonably meaningful sense, can have a dimension of 2.8, 2.3. What does this matter for these robots? Well, one example is navigation. How do they get through the body, find out where they're going? And that brings me to the research example I wanted to talk about. When research is presented, usually you just see the final result. Everything's all wonderful. What I'm going to do a little bit here is pull back the curtain a bit and show you some dead ends that didn't work out. That's more like a research project is at the beginning, when you're not sure where you're going to go. I'm going to be focusing on short-range navigation. These are the kinds of things we learn as toddlers. How do you walk straight in a hallway? How do you sort of not bump into obstacles and don't wander into some interesting room and never come out? Short-range navigation. In the case of these robots, this is dealing with navigation in small blood vessels. How might we go about doing this? Well, we're visual creatures. The most natural thing for us to think about is we'll use vision. And that's what we see in the stories. Unfortunately, microscopic robots are likely to be visually challenged. First of all, it's dark in the body, so they need a light source, they might have like a flashlight. And that uses energy, which these robots probably don't have a lot of. Second, it's likely to be blurry. Features on cells that they might be interested in looking at are smaller than the wavelength of light, so the light's not going to resolve them very clearly. And third, it's likely to be very computationally demanding. So imagine trying to run a self-driving car with a 1980s personal computer. It would not work very well. So vision, even though it's the most natural for us, I think is a poor choice. So then I want to think, well, what we're trying to do in these blood vessels, it's a complex three-dimensional geometry with all these branchings and so on that I mentioned, lots of walls and other objects, and that led me to think about caves. Now, if you've had a chance to visit caves, you'll see formations like this. Your guide might offer to show you the cave in natural lighting, in which case it's like this. It's a very interesting experience. If you've never done this, you'll see no matter how long you wait for your eyes to adapt, it makes absolutely no difference. Eyes open, closed, absolutely no difference. A really interesting experience. But we know there are animals that do just fine navigating in caves, such as bats. So that led me to the second idea, second thing to try, navigate with sonar. Bats do it in caves, maybe the micro-robots could do this in blood vessels. And so the idea would be the robots give out these sounds just like bats do and look for echoes and try to figure out what's going on there. I'm going to give an example. So the bat's air in rock, and in the case of the robots, blood and tissue. Imagine they emit an acoustic pulse, and let's see what happens. Get this to work. There we go. So the speed of sound in rock is very much higher than in air, so that's why you saw the sound go very, very quickly. The air gives the air versus the rock gives a very nice echo, but when they look at the difference between blood and tissue, both of which acoustically are more or less like water, you could probably only faintly see the echo there. And so that means if we're going to use sonar to have a detectable echo, you have to have a really strong sound pulse. And again, that means you're using a lot of energy from the robots, which they might not have, and also large intensity sound could damage nearby tissue, and you don't want that either. So that led me to conclude both these choices are not such great things. What might we use for a better navigation method? Well, ideally, we'd like the robot not to have to emit a signal. It would be nice if it were like when we go outside and we walk around in the daytime, the sun provides the light. We don't need flashlights. So that led me to this fish. It's a blind fish that lives in caves and pools and caves and navigates just fine based on how the fluid forces are on its skin. So then I wanted to evaluate that for micro-robots in a simple context. You put a robot in a vessel, this is all in simulation, and have the fluid move it, see what the forces are like. And this gives you an idea on the left, variations in pressure pushing in and out on the robot, and on the right, forces along the surface. I'm going to give you an example of a robot moving in a branching vessel so we can see how the pattern of forces changes. As the robot moves, the fluid not only pushes it along but also rotates it. So this green line indicates the orientation so you can see the rotation. And then I'm just going to zoom in on this box to show you what that's like. So here shows from the point of view of the robot what the fluid flow is like around the robot and the variation in pressure, and those lead to a pattern of forces on the surface of the robot. And you can see how this changes as the robot gets closer to the branch and starts moving into the smaller vessel. Okay. So now machine learning is all the rage these days, so this is an obvious case for that. You take many vessel geometries and robots and the positions and so on, and their corresponding force patterns, figure them out. This is all in simulation, and then you'd want to figure out, given if I have the force pattern, what can I tell about where I am in the vessel, how fast I'm moving, what direction is the wall if I want to get to the wall, and so on. It turns out, this is where the physics actually comes to our advantage. Small scale fluid flow is smooth and regular, not like the turbulent fluid flow that we encounter at our scale. And that makes the computation and doing the interpretation a lot simpler than what these fish have to do. So the conclusion here is this would be great for robots with not so much great computation. They don't have to be as clever as fish in interpreting their world. One sign of a productive research direction is there's always more questions. And here I've listed a couple of them. And then one of the skills you need to develop as part of research is decide, when am I done? When do I have enough to finish a project, or for that matter, a PhD thesis? You can always do more. Now that was the research project, a particular example that I wanted to tell you. And now let me give you some ideas of, well, how might you go about exploring alien worlds, whether they're these molecular machines or some other unfamiliar environment that you have. And the one idea is, well, can you find animals that live in different worlds, different perceptions that can be helpful and that are relevant. So dogs with smell, bats with sonar, and so on. And there's a variety of books that will help you with that. One thing I do want to caution you about is getting your idea of a field from news media. A number of years ago, a journalist interviewed me about my research. The article was fine, but it had none of the caveats or limitations or uncertainties that I talked about during the interview. And what this means is basically the news tends to emphasize the exciting progress, and you'll get a misunderstanding of the state of the field if you just look at the headlines. Here's an example from a recent British news weekly on whether or not AI is helping biologists understand proteins better. And so if you see this, you'd say, well, it looks like I should, if I'm a researcher, I ought to start using these AI techniques, I'll probably publish more papers. And that might be right, but you have to look a little deeper to decide, well, is this a causal relation or is it just a correlation? For instance, it could be the more productive scientists are the ones that jump on the new technology more readily. It could even work the other way. Maybe these productive scientists published 30% more papers before, and then they got distracted by all the going and playing around with AI, and then don't publish as much. You need to be a little bit more careful on that. This question of cause versus correlation is a really difficult problem in science. The book on the left and its associated website has a variety of really funny, spurious correlations of things that have nothing to do with each other, and the one on the right is an academic attempt to help improve statistical inference by making a distinction between cause and correlation. It's not an easy thing to do. Another thing that comes up in the news is we remember dramatic stories much better than, say, a boring list of facts or statistics. And so the news often tends to present an exceptional case as if that's the typical one. You read a headline, a new drug cures cancer, some particular person's cancer. Well, that's great, but it might not say, is that one person out of 1,000? The notion is that many of these strange and unusual events get really amplified in the news, but you have to realize that unusual events can happen all the time if you have a large enough population. So this book is a really good introduction to that, and the example is I buy a lottery ticket and I win, I'm really surprised. But millions of people buy lottery tickets. I'm not at all surprised that somebody wins. And you could have a news reporter go to that particular person and say, well, how did they pick their grandmother's birthday, and all sorts of various things. Had nothing to do with actually winning. It was a random, but you would have to make a nice news story around that. I'm going to suggest some tools better than just looking at the headlines. Three tools: guess, check, and switch. And what I mean by those is, first, when you're exploring a new world, try to get the lay of the land. Informed guessing is a good way to do it. On the left is a book about basically guess estimation problems. These are also called Fermi problems. And on the right is a textbook of a course. It's available online. It's, at MIT. It was also taught at Caltech, which goes into a bit more detail of how do I estimate what's important and what's about a subject that I'm not familiar with. An example that I gave here in this talk was my estimate of the computational capability of these robots. Now, you've been studying for a while, you think you understand what's going on, maybe you do, but it's important to check your understanding with contrary evidence. And so what I did here was, I could have just assumed sonar works great for bats, end of story. But it was important to actually go and check that the difference of the physics for these micro machines could make a difference in that. I've had the privilege of working with a large number of interns and really enjoyed the project. One thing I try to get across to them is it's okay to change the question if you're getting stuck. Research is not like a homework problem. An example I showed you here, I started off thinking of navigation, just in general, but then focused on this short-range navigation. First, you got to learn to work as a toddler before you can do, sort of go to some other city around the world. Another skill is, and this might be kind of disappointing, is like mean to say, do your homework, solve problems. I had experiences in college physics class. We'd have a guest lecture, everything seems wonderful and clear. You go home then and try to do the homework and you're stuck. Why? Because we as students didn't have the experience of knowing which of the many possible techniques going forward would be the one leading to the path, whereas of course the experienced professor did, and that's what he presented. So that's part of why I tried to show you when I was this example of the navigation, these false directions. I started with vision and sonar, and they seemed reasonable, but it did not work out. You'll be called upon to report your discoveries when you do make them. You'll have to explain in presentations. For me, in high school, debate and Model United Nations were really helpful for that. They were public policy topics, nothing to do with technology, but they got me up speaking, answering questions and so on. If you have opportunities for public speaking, I really encourage you to take advantage of that. One thing that I didn't appreciate until after graduation and working in industry for a while is something you have to explain to your discovery to a patent lawyer. And there's various things that are termed just like science and technology have their unfamiliar terms, so does the law. Obvious in patent law means something different than what I thought of. Once I've discovered something, it seems pretty obvious. This is hindsight bias. It's very easy after the fact. Oh, okay, I saw all these paths, I discovered this, and it seems pretty obvious, but you tend to forget all the dead ends along the way. So let me give you a couple of suggestions. This is mainly what I picked out from interns. People have different research styles. You try to find what's comfortable for you, and one good clue is, what is fun? What do you find engaging? Learning about fields, it can be very much from an inspiring teacher. And then I'd like you to expect change. Technology is constantly changing. You might end up in something that's not what you started with. And basic science and math are really good foundations. So to summarize, molecular machines and micro-robots, potentially significant applications. They're a way to manufacturing technology. It's somewhat like the situation with transistors. It took decades before we got to the point of having photolithography. And for alien worlds, they're all around us. They're in plain sight, but we just don't see them. They have unfamiliar properties. It can be a great source of new ideas and technologies. And now I'd like to take questions. Very good. Thank you.
Thank you so much. We have time for a couple of questions.
So you mentioned for these machines that go on like the blood cells, you mentioned they like get a reading of the forces. How do you like measure the forces? Like what sensors do you use that can measure like forces on a nanoscale?
So there are these materials called piezoelectric materials that when they slightly compress, they make a voltage. That's one way. Another could be you could have like a piston or a little like hair, if you like, that sticks out and like cat whiskers. And they push, and that distortion is something that can be detected in the robot. So a variety of it, this is molecular machine engineering. You need to figure out what kind of molecular machines would be good for sensors, for computers, for locomotion, for all these things. It's really a good field. Question?
You explained that in Israel they had like microscopic robots or something. Could you explain that a little bit more?
So this is the field of DNA robots. So DNA, you might know that the two strands of DNA, when they're complementary, they stick together, and when not complementary, they don't. And biology uses that for cell reproduction and so on. But people have engineered that. You can make your own DNA strands that will stick together and fold up in precise ways. So people use those, and then you add some things on the sides that say when they detect certain chemicals, they'll change how they fold. And that's the basis of DNA robots. And this Israeli group took a collection of that and reproduced a scenario that was in the science fiction story. That was mostly for fun.
Yeah.
Does that help?
Like, what was the scenario, though? That's what I'm like...
Oh, so are you familiar with Asimov's 3 laws of robotics? Have you heard of those? So that's his famous thing in his stories. And this, the idea is that the first law says the robot can't harm humans. The second one, the robot has to protect itself, and the third one to obey what humans say. And this was a scenario in which some of this robot was getting a little bit confused, going back and forth between what the priorities were on these laws. It's a fun short story, and amusing that then they could reproduce that scenario in the context
Yeah,
of the
that's
DNA.
really cool. Thanks.
I was just gonna ask, or we were gonna ask, hypothetically, if there were these robots, if they stopped working for some reason, would it be harmful to anyone's bodies or anything like that?
So that certainly, safety, of course, with any medical technology is something you'd have to look at, and so you'd have to worry about, when I design these robots, can they become in a if they stop working, do they become a fail-safe mode where they're not activating the immune system, they're not causing any problems, or maybe you need other robots to go and find them and take them out. There's a whole variety of possibilities and work that needs to be done to address that kind of question. But
I
it's a
think
very
our last
important
question will take over here before we switch.
Okay, if you had a vial of these micro robots and you drank it, what would it taste like?
It would depend on what you've decided to put on the surfaces, because that's what our tongues would be sensitive to. And most likely what you're going to try to is engineer these surfaces so that, say, they're invisible to the immune system, and also that the robots don't stick to each other. So you have a variety of those things, and those will be some shaped molecules on the surface. I don't know what they're going to taste like. Hopefully not too terrible. So if you did need to drink them, that would be the easiest way to get them. Put them in your tea or something.